which you don't, well, you kind of do, but you could cheat by just knowing you go over one, up one, but that's fine. I'm just trying to give you a general idea. If this line wasn't so pretty, because it is pretty, it's slope -1, but if we didn't have that, then how would we do it? I would probably scrap this. I'd go to this right here. So just pick one of those points as your x1, y1. You have y minus, let's pick this one. This is an easier line, easier piece to work with, right? So that's going to be y minus what? 0 equals m, which we said our slope was -1, x minus 5. And just clean that up, and we have y is equal to -x plus 5. Got it? So if we live on L3, right, if you are a point on L3, here's what I can tell you about that point. It has some x coordinate, right? And the y coordinate is always -x plus 5. That's the relationship between those 2 points. Whatever this is the y has to be that. Yeah? Questions?
Where did you get the x?
This? Just I'm picking an arbitrary x. If I come out here and I say, hey, okay, pick an x, that takes me to here. Now what's the y coordinate going to be? To live on the line, the y coordinate has to follow the equation of the line. So the x was arbitrary. Okay, so now what we'll do is, just like we did before, all the points on this line L3 look like this, x, -x plus 5. And we do have a restriction on x, right? What's the restriction on the x that I plug in to be on this line? Smallest x I can be is 1, the biggest I can be is 5. So I still have this restriction. Plug this into that. You get what's f of x comma -x plus 5. This is 3 plus x times the y, but the y is -x plus 5. And then minus x, and then minus 2 times -x plus 5. You see, that's just the original function with all the y's replaced with -x plus 5. Anybody have any idea what type of function this is going to be when you put it all together? It's going to be a parabola, right? Because I showed you the picture. When you plug that line in, we got this black parabola, didn't we? This better turn out to be a parabola. It's going to. It's, let's see, 3 minus x squared plus 5x minus x plus 2x minus 10. Clean it up. -x squared, -x squared. How many x's do we have there? 6. 6 x's. Constant, -7. Boom, there it is. So I mean, this is really cool, I think. I don't know. I think a lot of things in math are cool, so I don't know how that translates to you. But what we know right now is when you plug this line in and you throw that into this function and you look above, like if you're standing there on this line, you looked up, it would be a parabola. And it would be opening down because negative in the front, it's going to open down. And so what we want to know is what's the maximum and minimum values of this on this closed interval. So now the derivative is going to matter, right? We're going to take the derivative of that. So what would the derivative of this x comma -x plus 5 be? -2x plus 6, right? And then from there, you set that to 0. F prime equals 0. Well, that's going to be -2x plus 6 equals 0. So x is 3, right? X is 3. So we actually have a critical number this time, don't we? If x is 3, can you tell me what point that is over here? Come back to this. If x is 3, where are you? 3, 2, right? 3, 2. Plugging in 3 for those. So this means, this implies that 3, 2 is a critical point. Understand where the 3, 2 came from? Yeah? So what I do now is that's the only critical point I have. What I need to do now is I need to look at this function at this point and at what? X is 1 and X is 5. See, I haven't done that part yet. So I'm going to write those out. So I'm going to look at what happens when I replace the X with 1. So put 1 right here, we get 1, 4, right? Replace the X with 5, I get 5, 0, and then replace the X with 3, I already know what happens. I get 3, 2, right? So I'm taking the two endpoints, and I'm taking the critical point, and I'm going to plug all those into the original function. And let's see what we get. We already know the first two, don't we? Because we already did those, didn't we? Didn't we do that point already? Didn't we do that point when we did L1, L2? What were those? 1, 4 was -2, and then 5, 0 was 2? Oh, it was the other way around? It's 2 here? Yeah, 2 and -2. Okay. And then what about F3, 2? We have not done that yet, right? We've never plugged 3 and 2 in there. So let's go ahead and do that. Plug 3, 2 up there. We could actually plug, no, that's the derivative. We could plug it into the parabola, but I'm going to just plug it back in up here. So 3 plus 3 times 2 minus 3 minus 2 times 2. What do we have? They're both -2? Okay, well, y'all just say something. I've erased it from the board. I don't remember what it was. You're the one who has it written down. Okay, so negative, negative. Wait a minute. Hold on. 1, 4. Oh, yeah, because 1, 4 was up here at this one. Thank you. Okay, so what do you get when you plug in 3, 2? 6, 9. Those threes cancel. 5? No. 2. You get 2. You get 2. Okay. We've gone around the boundaries, right? The whole boundary we've taken care of. We looked on the inside. We did find a point on the inside. What was that point on the inside? 2, 1? Yeah? So let's put this all together, all right? Let me put all the points that were important to us together up on the board. We had, from the first part of this problem, so I'm on step 3 of this. I'm going to compare now. I have, from the first part of the problem, I got this point 2, 1. From all the different lines, L1, L2, L3, I wound up having these 3 corners. And this one up here, which was 3, 2, right? Does that cover everything? Is that all the points we got? The one here, the 3 corners, and then that 1, 3, 2, 1 right here. Right? That's all of them? Yeah. And now let's just, we already know all their values, right? Let's just write their values down. Oh, we never got, which one did we never get? 2, 1, right? We never got that one? This one was 2, I believe. This was -2. This was -2. This was 2. Find the value at 2, 1. Plug in 2 for x and 1 for y. 1? All right. That's everything. Now we just need to draw our conclusion. No questions? What is the maximum value of this function on this closed bounded set? 2. The maximum value is 2. Where does it happen? Here and here, right? At two places we have the absolute maximum occur. Where does the absolute minimum occur? Two different places, right? The value is -2. So there's different ways we can actually write down this conclusion, right? We can just simply state it, write down all the points. I'm going to kind of show you both ways. The absolute maximum is 2, all right? The absolute minimum is -2. Now, if I want to put where they happen, then I could just list the points as ordered triples. I could say 1, 0, 2, and 3, 2, 2. This is where I get my maxes, right? And then I could say, let me see, 5, 0, -2, and 1, 4, -2. Those are where I get my minimums, right? You should be comfortable stating it either way. The reason why we want to just be able to say what the max is and the min is because a lot of the problems that we would deal with that are like real world or like word problems, that's all we're looking for. And in other problems, you want to know where it happens. And so you would want to know more information like this. Okay. Wow, that only took about 40 minutes. May I? I think what we'll do on this one is we'll do all the maths first. After we're done with all them, you ever hear like a lot of Europeans say maths?
Yes.
Heard that? Okay. Yeah. All right. So we're going to do all the maths first. And then after that, we'll compare it with the picture. All right? So we have an absolute maximum, and we're looking for the absolute maximum minimum value of this function. On the rectangle, D is equal to the set of x and y such that x is between 0 and 3 and y is between 0 and 2. So we have to understand what that means first. This is set notation. It's all ordered pairs in two-dimensional space where your x's are bounded between 0 and 3, your y's are bounded between 0 and 2. What does that look like in two-dimensional space? Rectangle? X values are between 0 and 3. So all I know is that the points, the x values have to live between here and here, right? So your x's could be anywhere in here. But your y's have to be between 0 and 2. So it could be anything in here, right? And so what you need is both of them together, which is where they intersect, which is this right there. So we're looking at this rectangular region. It's closed and bounded, right? As long as these inequalities were included the equals, right? Then it includes the boundaries. All right, there's our region. How would you like to go about this? What should we start with? Find the critical points from what we did last class, right? Set the partials equal to 0. All right, so go ahead. Do it. I'll do it up here. I won't say anything. I'll just kind of. I don't like what I did there. Y'all got the partials yet? Set to 0? Got a solution? So your first partial set equal to 0, all you get is a relationship that x has to be y. That doesn't tell you enough. But the other partial equal to 0 tells you x has to be 1. And if x has to be 1 and y has to be x, then y has to be 1. So that's your critical point. Now, we need to double check to make sure. Does it live in here? It does. It lives in there. So check. We will plug that into the function. You want to plug it in now? Just may as well like figure out what the value of the function is now. We don't know if it's a max or min or anything, but let's plug it in. F of 1, 1 will be, is it 1? Yeah. Save that for later. I've had students on tests, the one that you're going to take in class next week, I've had students on tests forget to do this step. They do all the boundary, they move around and all that. They forget to do the partials equal to 0, and I take off a lot of points because this, you have to check that number. I mean, you have to check that point. That could be the highest point, could be the lowest point. If you forget about it, then that's like, it's like forgetting to check one of your endpoints back in Cal 1. You're just like checking part of it, not everything. All right, that part's done, yes? Now, we're going to move around this closed bounded set. So we're going to break it up into how many different pieces here? 4, okay? 4 pieces. So here's what we'll do. Let's define this to be L1, and let's go clockwise. L2, L3, and L4. What I'd like for you to do is let's let these tables right here, these 2 tables, we'll do L1, okay? These 2 tables will do L2. These 2 tables will do L3, and I will do L4, okay? So y'all work out L1, y'all work out L2, y'all work out L3, I do L4. And we'll talk in a second. You do your work, I'll do mine. And y'all can talk to each other. Got to turn my microphone back on. Oops. Oh well. Shit happens. Can't do anything about it now. I even, when I walked out, I almost reminded you, I was going to remind you to tell me to turn it back on. Okay, it's on now. First quadrant, and then I have to be inside a circle of radius square root of 3. So here's root 3. Here's root 3. Everything in there, including the boundaries. Right? So we start by first looking at the partial, setting them equal to 0. So what's the partial of f with respect to x set equal to 0? That's y squared is 0. Next, partial with respect to y equal to 0, which is 2xy must be 0. Well, this already tells me that what? Y has to be 0 in order for that to be true. And over here, shit, what does this mean? How do I make this one true? This says y has to be 0, right? So over here, does x have to be 0 for this to be true? No? Why not? Because if y is 0, then it doesn't matter what x is, does it? If y has to be 0 to make that true, then y has to be 0 here, and then you can let x be whatever you want it to be, right? So we actually have x is free. Call it free variable. It's free to be whatever it wants to be. So we have an infinite number of points that satisfy this, don't we? They all look like this. They all look like that. Do you agree? Any point that looks like this will satisfy these two equations. Thank goodness, though, these points coincide with what? This is your x-axis, isn't it? That's what this is. This is your x-axis. And it turns out that that's the boundary of one of my sides. So we got lucky that the only critical numbers or critical points we're going to get from this right here is actually what we're going to be looking at in just a second. So what if we didn't? What if we didn't have that? What if that was somewhere inside here? Well, then we would have to plug these into that and figure out what happens. It would be almost the same exact story. We plug those in, figure out what that is, and then take the derivative. Okay, so let's move along these. L1, I'll call this L1, will be along this edge. L2 here, I shouldn't call that L3, right? It's not straight. So I'll call it C1 for curve 1. So I'm going to go around L1, L2, and C1. I think we can move quicker through this one. On L1, tell me what the points look like. X0, what's my restriction on x? 0 to root 3. Okay, plug in x0 into the function. Oh, come on. 0. Which means I can stop. It means that if you plug any point in along this edge, the function spits out 0. Right? That's what that means. I don't need to keep on doing any work, right? Take the derivative of 0. Go ahead. I mean, right? I mean, there's no need to do this.